All right. Okay, let's get started. So just before we dive into your question here, in a very soon, let me just point out to you something very important. So I just made a earlier announcement today, just not long ago. So you may have not seen that. That's okay. I'll just point out to you and go over that with you very quickly. Nothing big. So it's basically just about the cover page, which you will receive on the the question booklet on Sunday. So the information there, you can. I will encourage you guys to read it over. Pretty short, just to be clear about the policy. Okay, about your data sheets, nothing surprising. You can computer type, you can handwrite, as I said in the last class. But just make sure the font size is actually not too small. The minimum 10 points, and no margin. No margin restriction. You can put everywhere on the single side. Okay, that's just the thing as I said in the last class. And no calculator. All right, and also, and that means, for example, if there's any formula you believe you will need, feel free to put it on your data sheets. But I think for any calculation you will need to do, they should be simple enough. You don't need a calculator. All right. All right, so you will be given question booklet and also answer booklet for both the exam. Just make sure you fill out your information in the beginning, and then I will remind you, and you want to return both of them at the end of the exam. It's obvious. And for your question booklet, you can feel free to sketch or do whatever you like on the question booklet, but just remember, only anything you write on the answer booklet will be graded. We're not going to find your answer in the question booklet, okay? And then there's something also important. So the order in which you put down your answer on the answer booklet should really correspond to the order they appear in the question booklet. So your answer booklet should really be question 1, part A, part B, part C, and then question 2. For example, if you want to temporarily skip some parts or question, that's definitely fine. But you have to make sure you reserve just enough white space over there on the answer booklet. And make sure you got enough white space when you come back here later, you can still answer them, right? So the order is very important, right? Just make our grading much more effective. Okay. And you can write your answer in either a pen or pencil, but please don't try anything other than black or blue. It just makes it so much more difficult. If you use colors such as red, green, or purple, it'll be very difficult for us to recognize your answer. So please make sure you don't really write anything other than black or blue. And please don't write in cursive. It's going to make it even more challenging for us. Please no cursive. Just spell out your answer properly. Okay. We understand that there will be time constraint. Your writing may not be as ideal as what you would do normally, but no cursive, please. We'll try our best to recognize your answer. Okay. And yeah, do not sketch on the answer booklet. So anything you put on the answer booklet is going to be for grading, right? So any sketch work is not going to be graded anyway, so you don't want to waste the space. We will have some spare answer booklet during the exam as well, but I don't think you will need it, but we'll have it ready just in case you would need it. All right, so that's about some administrative side for the exam. Okay, so guys, how about this? Before we start with the review session itself, is there any general question you might have? Go ahead. Anyone? You can feel free to type on the chat, or you can just, okay. Essen, go ahead. You might be muted. I cannot hear you. Hello, Essen? Are you speaking?
Am I
You're good now. Yes. Go ahead.
Okay. No, I was just wondering. For the monotonicity rule, right? The
Yeah.
first time you use it, when we have to select the hypothesis that we would like to use for the rest of the proof.
Yes.
Is there any tips on which hypothesis that we should be looking for? Because I sometimes struggle with selecting the first.
Okay. Okay, this is more like a proof strategy part. I can try to answer that as much as I can, more generally. Okay, that's a good question here. I'll try my best. Okay, so Anson's question basically go like this. You might be given maybe some kind of like a sequence over here. Of course, usually the goal itself is going to be a single line, right? Just a single predicates. But it's the hypothesis part that's going to be quite giant. It's very possible. For example, if you look at maybe one of the deadlock freedom, or maybe one of the relative de la freedom or the invariant preservation sequence, usually they are quite big because the hypothesis there by the rule is going to accumulate axiom, invariants, guards, etc. So inherently it's going to be big. But when you start with this, so what I said in the class since the beginning will be you can try monotonicity over here, but now the question is how exactly do you choose to go from maybe here into something that's actually much smaller, right? So I would say once you go from here, you want to have something, maybe hypothesis will be reduced to only this small part over here. In general, okay, I would say before you even start writing anything down for the proof, I would suggest this is where you might need some quick sketch about what you can do. I'll give you one example in just one moment, okay? So let's say you may want to start with, I would say step number 1. You want to examine what's exactly to be shown as provable. Examine what's to be proved. More specifically, you want to look at exactly the structure or the variables that's being involved in the goal, right? Specifically, you can say maybe the structure. For example, the structure could be something about implication, or something about larger than, or something about equals, etc. That's what I meant by structure. Number 2, which is in some way more important, is about the variables being involved. So also the variables. Yeah, for example, let's say if the variables involved is only about x and y, in that case, you may just want to first start by looking at what are the equations or predicate that's to do with x and y. First of all, it doesn't really mean you gotta use all of them, but at least some of them will be useful for your proof. Okay, so and then I would say step number 2, you kind of select. I would say in sketch, right, or in your mind. So up to now, I'm only talking about how you're supposed to do your planning before you actually start writing. Because once you start writing, you should be more or less kind of confident about how you should really proceed. At least have some rough plan. So select in sketch I would say the predicates. I shouldn't say equation because they don't need to be equations all the time. The predicates related to the variables, which you identify in step number 1 over here. All right, and step number 3 is from there, you try to see how these hypotheses are related to the goal. Right? Once you identify all the relevant predicates over here, try to see how they are related to the goal over here. And then that's something I'll try to describe how I would think about it to see if that makes sense to you, right? So the way I say connected, right? Related to. So you want to maybe look at your data sheets right now. Look at your data sheets. Okay, of course, you can look at your data sheets and then look at the inference rules that are applicable. And I would say in the sketch phase, you don't necessarily have to know exactly in what order you're going to apply the inference rule. You just want to see if at least the sequence may be provable. Because the question itself might say, show whether or not the sequence is provable. In case you really try your best to try to figure out exactly what's going on, but you believe that the sequence that's given is unprovable, in which case you don't need to show any proof. Just say it's unprovable and give some justification. But if you really believe some inference rule on your data sheets can somehow work out the connection between the hypotheses to the final goal, you know there's a proof for you to write. And then you can kind of sketch some steps on your sheets, and then you can start moving on with the actual proof and by writing on the answer booklet. So I would say all I said about 1, 2, and 3 are really to be done before you start the actual proof that's going to be put on your answer booklet. I would say maybe spend a few minutes depending on how confident you might feel. If you really think that particular sequence is a very difficult one, you may want to maybe skip that temporarily, because it's not like every question on the exam is about sequence proof. There will be some, but not every one of them. So if the sequence is something that you can identify number 3 right away, just go ahead with the proof and finish that, right? If it's something that you find that a little bit too demanding at the moment, you can maybe come back later and spend a little bit more time planning this. But I would say 1, 2, and 3 are definitely some necessary steps for you to really finish before you actually start the actual proof. SM, does that kind of help? I hope.
I think so, yeah.
Okay, yeah. So, okay, let me just give you one more example, right? And then we can move on. Okay. It's an important question, so that's why I definitely should spend some time, just repeating what we kind of covered in the lecture earlier. But let me give you just one example here. Okay, let's take one of them. Okay, if you go to your slides over there, okay, let's just find one of the proof. We don't need a complicated one, but we can just try to look at. Maybe the first one will be enough, or maybe the reasonably complicated one. How about de la freedom? Okay, how about this one here? Let's say this one here. Let's say this is what you're given. Not very complicated, but here you can start with step number 1. You can see that this particular goal over here is going to involve both N and D. But this one, of course, you can see N and D are covered in every predicate over here. But I would say typically when you only say the types of the variable, like a D is a natural number, N is a natural number, they might say something useful, but not the most useful. So you may want to look at other more elaborate equation that say something more about the types of the variable. In this case, N less than or equal to D is the only one that's not just about the types. So that's why it ends up, we actually have chosen it after monotonicity, which is over here, right? And then after that, once you got this, you want to think about what inference rule might apply in order for you to go on with the proof. So now I can see that part of the goal, goal over here is N less than D. Somehow it matches with this guy over here. And also this one here maybe somehow can be linked to both of them, right? To some extent. So that's why you can now kind of think about how you can split the hypothesis, and we know that we got O or L. So whenever you see any disjunction for the hypothesis, you know that you potentially can split the hypothesis into 2, right? You can separate them into 2 separate sequences and go from there, each one of them. Versus if you actually got disjunction for the goal over here, you should not really split the sequence, but you can only selectively choose one of them. For example, this one might be a nice one to choose because this one here matches N less than D right away, right? In etc. Yeah. All right, so that's something for you guys to think about, right? You can definitely try to apply this kind of a strategy, for every proof exercise you try to do between now and also Sunday exam. All right, Essen, any follow up for you, or you're okay?
I think I'm okay. I think I'll probably just need to practice a bit more.
Yeah, practice a little bit more. Yeah.
Yeah.
I would say start with, actually we got many proof exercises so far. If you want to, let's say, practice proof specifically, you can definitely feel free to use of these PDFs over here, right? So all these are all the proofs that we cover in the class. So you can maybe start with a simple one and then go with a more complicated one by applying the strategy. Of course, there might be some extra strategy you might find working for you specifically. That's something you want to think it through, before the actual exam.
Okay,
all right.
thank you.
No worries. All right, guys, next question.
Professor?
Yeah, Billy. Yeah.
Questions in exam?
Yes, there might be some rodent type of question. So, for example, I might give you some problem for specification. And for example, let's say the FTP protocol, right? That's part of your practice exam questions. I might give you a new problem like a FTP. I think maybe for most of you, that's the first time you're seeing that. So I might describe informally what the FTP is supposed to do, and then I will divide the question into different parts. And maybe the first part, I'd say, okay, now for this particular invariance, I want to specify blah, 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 something. I'm going to specify informally in English. And then I would say invalid rodent syntax, write out the invariance. I'll be very explicit if you are required to write in rodent syntax. So that's definitely something you want to get prepared for. But I would say for most of the common operators, for rodent, I'm pretty sure you guys are pretty familiar with, given that we already got, two programming tests. If there are certain, for example, relational operators, let's say overriding, domain restriction versus subtraction, for example, you are still confused about it, or maybe injection, surjection, things like that, feel free to put them, on the data sheets. They wouldn't occupy that much space. You can definitely handwrite. Yeah.
Thank you.
Yeah. Yeah, bottom line, you will definitely be given some rodent syntax question. Well, I wouldn't ask you specifically about the syntax. I may not. But I might give you a problem, but the answer is going to be required to be specified in rodent syntax. So you got to make sure you know how to express yourself in rodent syntax. Yeah.
So are we going to have the rodent help the syntax sheet?
No, you're not gonna be given. Like an event-based summary, right? You're not given that. Yeah, I'm afraid you will have to put the most unfamiliar syntax of rodent maybe on your data sheets. Okay. From Emra from the chat, how to apply not L in? Okay, sure. Okay. Emra, what's the page number for slide? Is it 23? Can you tell me the slide number? You said lecture 23, but if you can tell me the slide number, that will help. iPad notes. All right, sure. Tell me to stop. Not this one here, right? This one? This one? No, here, right? How about this one here? All right, good. Okay, this one here, and you're talking about not L, okay, not L, which was, I can make a screenshot, one moment. Approach one, not L, I see, over here, right? Okay, sure. What I will do is, let me take a screenshot over here, okay, and that one also includes the not L, and I'm going to explain that, just give me a moment, let me get prepared. Okay, let's do that. Okay, let's now switch over here. All right. So your question was specifically about the not L over here. Okay. But before that, let's review not L inference rule, which is over here. That one is to say the not appears, the negation appears to the left of the turnstile. So that means when you actually got not P over here, right? You can, so let's say to start with, you have some sequence where the negation is on the left of the turnstile. You can certainly move that into the right hand side of the turnstile, but at the same time you can switch the original goal back to the hypothesis over here, kind of swap the hypothesis and the goal. And whenever you go from the left to the right or the right to the left, you got to negate the predicates. So this one, as we said in the class, let me just talk about it one more time. So now think about not P implies Q over here, right? It's basically equivalent to not Q implies P, right? Not Q implies P. And this is something we call contrapositive, right? Though that's something you don't want to forget. Okay, so that's the contrapositive. So just to make sure I understand the rule itself, but let's now see how we can apply that, okay? So this is how we started with for that particular sequence. And you can see that here, this is a negation, right? Not equal to. Another way for this one, you can, okay, let's say this one here. for the rewriting, you don't really have to justify. This one is very easy. That one is okay. So this one here, this will be as if we wrote not the case green equals red, right? So you can think about this part over here, not P is like the not P over here. All right, so what we can do is we can now try to switch this one to here, in which case we get rid of the negation. And then for this one here, we can now switch that to the hypothesis. In that case, we got to negate 1 equals 0. All right, that's the overall picture. So let me just try to do here. Okay, so now here, after not L, so what we will have is, so we still got the original one, green equals red, and this one here, right? Let me just kind of rearrange the order a little bit. So we still got our green equals red, and also ILTL equals green. And then we got our turnstile. Okay, then now let's now specifically talk about those two. So we got this one here, and we got this one here, right? So now this one here, if you put it in the hypothesis, is going to be 1 not equal to 0, right? And this one here, if you put its negation in the go, it's going to be green equals red. Am I doing something wrong here? Let me just take a look. Okay, so green is not equal to red, so if we move that, that will be green equals red over here, and then green equals, okay, got it, yeah. And then after this one here, and what we got is this. What we can see is this one here, green equals red, because they are different members in the color set, right? Asen, are you more talking about which one? Sorry, if you can speak up, that'll be easier rather than yeah. If you don't mind. This one here, sorry.
For the negation, right?
With negation, yeah.
Like green equals red.
Mm-hmm.
I was just wondering why is it not like not green equals not red? Is it because it's just one predicate? Or?
Yeah. You mean talk about this one here, right?
Oh, sorry, no, the one above. When you distribute the negation.
Oh, this one here. Yes.
Yeah, like are you distributing the negation?
Yes, exactly. Yeah, so this one here, I'm just trying to make it a little bit more obvious to you about negating it. So you can think about, of course, when you try to put this one here into the go, you're going to put its negation. So if you put a negation into not equal to, it's going to be equal to. But
right, so it doesn't change the green and the red, right?
It doesn't change the green to red. No, I'm just saying. So somehow, but once you reach this predicate over here, right, in the go, we know that this one here, it just evaluate to false because green cannot be equal to red.
Right.
Okay, good. And then over here, this one here. And once we apply this not L over here, we can see that how do we move on further? But at least that's about how you can apply the rule. But it turns out, what's gonna determine this predicate being provable is you can look at this one here. Because green equals red here, well, we can apply some arithmetic, right? Let's say arithmetic. This one here, we know that it's false, right? Green is not equal to red. And also this one here, we also know it's false. And this one here, we cannot simplify any further. And for this one over here, 1 not equal to 0 is actually true, right? But as long as we get this false over here, we can already prove it because I think one of the inference rule is to say if you got false as the left-hand side, then you just prove the entire sequence. So it turns out not L over here is not entirely necessary, but I just want to show to you as a first step of applying not L, which is sometimes maybe a necessary step for you to make use of the negation. But in this case over here, I think the two lessons here, number one, when you actually apply not L over here, you're just going to put a negation of the go into the hypothesis, and also to put the negation of the hypothesis into the goal over here. We do that first, okay? It's the first step. And then after that, you can see how you can proceed. But in this case, we can simply use the existing one over here to say that one is already false, so the whole sequence is going to be provable.
Yes, sir.
Yeah.
Can we apply not L on any one of the hypotheses as well?
That's a good question, Billy. Yes, you can say that, yes, because for any predicate, you can always rewrite, think of it in a form that's not something, right? Well, because of double negation. That's a good question here. So for any hypothesis like a P over here, you can always rewrite it into not P. So now you always can have a negation form for the hypothesis. Yes, indeed. So that means you can think about the not L is really a rule for you to really move any hypothesis into the goal whenever you think that would be the need. But that's kind of up to you.
So I mean, like you use green not equal to red. So we could have used not L on green equals red as well.
You mean this one here?
Yeah.
Yes, you can use that potentially too. Yes. So because for this one,
then it will be hypothesis. Like you can just use hypothesis inference rule to prove it.
Without inference rule to prove it. You mean? Oh, I see. Yeah. So here, sorry, say that again, Billy. I don't quite get what you mean.
I mean, like if you use not L on this,
Yeah.
this will become
Yeah.
green not equals to red in the proving part, and then you can, like, using monotonicity, you can use hypothesis, or you can just say false.
Yeah, exactly. Yeah, that's right. That's just another proof. So what you're saying is, if I use a not L on this one here, so that means I'm actually going to put green not equals red in here. In that case, this one and this one here match, so you can use hypothesis. Yes, that's right. That's just another proof, indeed.
Oh.
Yeah. Yeah, but I think you made a good point. For not L over here is a very general rule. That means you can identify any of the hypotheses in your hypothesis section and then put its negation into the goal instead, if that helps. Okay?
Yeah, thank you.
No problem. But how do we apply contrapositive although n has higher precedence than implication? So Emerald, what do you mean by that? Okay, so I'll wow. Okay, over the chat is a bit it's a bit harder for me to read, but anyway, so I'll try to guess what you're trying to say. So not L over here. So you're right. Maybe we are targeting this one specifically. You might have some other hypothesis over here that's correct, and then we say that comma is actually for conjunction between the goal or the between the hypothesis. So I think the general proof about this one over here, that's something we are not exactly covering, but I'm pretty sure you can prove it. But one way to think about it is you're targeting this one specifically, which you can think of like contrapositive. But if you try to add any other additional hypothesis, I think in general it can also be proved, if that's what you're confused about. Okay, I presume it's okay. All right. All right, guys, next question.
In written test one,
Yeah.
we had a question where you were asking whether one of the ordered pairs is a subset of the set of partial functions.
Okay.
Could you explain why
Yep.
that was an invalid statement? Because in the
Sure.
answer you said that KLHS is not equal to RHS.
Let me get to your written test one first, and then let's talk about it. One moment. So you can tell me exactly which question it is. Written test 1. Okay. Okay, so give me one moment, I'll get there. Okay, there we go. So Billy, which question? Not this one here, right?
No.
Not this one, I presume. This one?
No.
Not this one. Not this one. Not this one.
No.
All right. This one?
Yes.
Okay.
So for this one part, I think the second part.
Sure, no problem. You're talking about this one specifically, right?
Yeah. A23, B46.
Yeah, yeah, got it. Let me. Okay, let me just take a screenshot. Yeah. And then I'll explain that. Give me a moment. Okay. Okay. So Billy, just to be sure, you're talking about this one here, right?
Yes.
Okay.
Yes,
Yeah, good. Okay, this one here. Okay, that one is not valid, correct? That's the answer.
Yes.
Okay.
Yes.
So here we're basically distinguishing between 3 possibilities. Okay, so let's say either it's valid versus invalid. Invalid, well, some programming analogy, it's not type correct.
Okay.
But I'll explain that. I just want to give you some overall picture first. And then when we say it's valid, that simply means it compiles. At least the types actually make sense. And within valid cases, we got 2 subcases. Either it's going to evaluate to true or false. All right, so these are the 3 possibilities, either true, false, or invalid. Okay, so now this case is going to be invalid for the following reason. If you only look at the right-hand side over here, so this is the set of all possible. You can see this symbol over here. It's a partial injection. Between these 2 sets. All right, that's pretty clear. And you can see this one here is the subset symbol. In order for this, well, given these 2 parts, in order for the left-hand side to be valid, it must be a set of partial injections, not a single one. But here, this is a single partial. This is a single function or a single relation. So you cannot really say a single relation is a subset of that. Well, you're basically writing something like this. You're basically asking whether X is a subset of, for example, X, Y, and Z. But this is not even valid. Because in order for you to judge whether something is a subset of another set, this something here must be a set itself. Okay, so, just to follow up very quickly, okay, how can we fix this, right? So I can potentially fix this by saying, why don't I just make it a singleton set? Then this will make sense, right? Or I can just put the surrounding brackets over here. So this is going to make the left-hand side a set containing a single relation. And then I can ask whether or not it's a subset of the set of all possible partial injections. So that will be some potential fix.
Thank you.
Okay, good. All right, guys, next question. Yeah, take your time. I'll wait. It's really your time.
Good morning, Professor.
Good morning. Hi, go ahead, please.
Yes. Could you just explain one more time the use of mainland pass and island pass?
Mainly. Oh, okay, sure. You mean the 2 variables, right?
The two variables. Yeah,
Of course.
The past, yeah.
Of course. You mean just in general, like intuitively, right?
Sorry?
You mean just like intuitively how they are used?
Yeah, how they use
No
the,
problem. No problem.
meaning.
Okay, I'll give you some resource. I'll give you some pointers as well, so you can also take a look. Okay. So Harjab's question is about ML pass and IL pass, the two variables. That's in the last lecture. Okay, so I'll let you know where you should really look at first, and then I'll go back to the notes and talk about it. Give me one moment. So when you study this part over here about ML pass and also IL pass for the lecture, so you should really, first of all, be clear that the reason we have to introduce these two variables is because the M2, the second refinement, actually diverges because we got a lifelock situation. So this is something you can review again. It's not really part of the question, but I'll just point out to you. You can take a look at, for example, this trace over here. That one shows to you potentially we can just get an infinitely interleaving between ILTL green and MLTL green. Basically, the flashlights, the traffic lights on the two ends of the bridge will simply keep flashing, right? So that's definitely something we would like to avoid from our model. So that's really the motivating scenario for introducing some new variables to regulate the traffic lights. So that's why we got the two variables. So for ML pass and IL pass, you can definitely try to read over the definition over here, right? So that's something I will encourage you to do first before you kind of start reviewing the how they are used. But I'm going to point out to you exactly, okay? Okay, let's now take a look at the iPad notes. Okay, give me one moment. I'll go back to that part of the lecture and I'll talk about it. Okay, there we go. Okay, so this is where we discuss it in the last lecture. Okay, so I'll just kind of look at the annotated version directly, but if you want to see how the annotation has been developed, you can definitely check out the recording from the last lecture. So we got ML pass and also we got IL pass. They are very simple type. They're more like a Boolean. You can think about 0 for false and 1 for true. Okay, so think about, let's say we start with here, MLTL green and ILTL green. So these are the two events that we wish to block from being interleaved indefinitely. In which case we get a life lock. That's something we want to avoid. So the way we do it is by this. You want to make sure the guard of each event, for example, for MLTL green, you want to make sure IL pass over here is actually 1. Versus when you try to do ILTL green, you want to make sure ML pass is actually 1. All right. So as part of the guard for each new event, you have one of these variables being there, meaning that whenever we change the value for IL pass, it's going to impact. Sorry, let me say that again. You can see MLTL green over here. As soon as this event occurs, you can see as part of its action over here, it's going to set ML pass to be 0. And as I try to point out to you over here, as soon as this one is set to 0, it's going to disable ILTL green right away. Hajab, can you see that over here? Just to be sure.
Yeah, I can see that.
Yeah, I think that's the most critical insight into using these two variables. You want to make sure as soon as MLTL green occurs, ILTL green is disabled. And also vice versa. ILTL green, as soon as it happens, is going to set the IL pass to be 0, which will effectively disable the other new events. So this is the way for us to really make sure whenever a new event occurs, the other one is disabled right away. So if you look at the tracing here, as soon as MLTL green occurs, it's going to set ML pass to be 0. And at this point here, ILTL green cannot happen right after MLTL green, which is the kind of divergence trace that we kind of exemplified earlier, right? So that's a critical insight. And then for the O events, MLL and ILL, 1 and 2, we talked about split events earlier. So for each one of them, you don't really have to disable the other one anymore. So you can still segment back to your 1 over here. So that means, for example, after several occurrences of the O events, ILTL green cannot occur, right? As long as you don't really have the indefinite interleaving between the two events, we will be safe from the life lock. So the most important insight is to see, if you look at the plot over here, every time if you got any new events happening, you're basically going to set one of the ML paths or IL paths to be 0. That's why their sum over here is going to decrease from 2 to 1, because we're adding basically, this can be 1, this can be 0, or this can be 0, this can be 1. In that case, when you decrease to 1, it's guaranteed one of the new event is disabled. So you cannot just have interleaving between these two consecutively, right? So that's the intuition. Hajab, was that okay?
Okay. Yeah, that was it.
Yeah. So I would say when you study this again, try to definitely look at how I build up the annotation for these. It wouldn't take long, this one here. And also try to convince yourself the tracing over here, especially after the occurrence of MLTL green, we effectively disable ILTL green. Similarly, as soon as after the occurrence of ILTL green, we also disable MLTL green. And then you can also look at the plot over here to see the trend, right? Essen, go ahead.
Yeah, just building off of that. There are two proof obligations that we discussed, right? For
Yes.
variance.
Yeah.
So I guess when we have to prove the variance, we have to do both proof obligations, right?
Yes.
The non-negative one and the decreasing one, right?
Yep.
Okay. Thank you.
Oh, okay, just verifying, no problem. Yeah. So yeah, no problem. So guys, okay, how about this? For variance, the most important thing for you to know, number one, you want to know about the expression itself, right? And then the expression itself, once you know them, intuitively, you have to know that whenever, for the variant to really work for your system, number one, for whenever a new event occurs, the variant value must strictly decrease. And then for any occurrence of the old event, it can either be increasing or stay flat, stay the same, right? That's kind of observation we talk about. That's an informal understanding. But the formal proof obligation is going to kind of formulate them, right, in a sequence. So this will be the var proof obligation, which tells you the post-state value over here after the event occurred, the new events, is going to be strictly smaller than the pre-states. So that means we're going from this here to here. So this will be the pre-states, this will be the post-states for the new events occurrence. So you want to make sure you're strictly decreasing the value for the variance. And the other proof obligation is about the variance being a natural number, right? Palmam, go ahead.
Hi, Professor.
Hi.
I had a question regarding the example final exam that
Sure.
you posted.
Of course.
Yeah. It's question number 6.
Sure. Let's now take a look. Let's now question number 6. Yeah, go ahead. Which one?
The very first one, I understand the answer, but
Yeah.
I had problem to formulate it myself. So like.
Sure, no problem. So I think the critical diagram over here to understand will be this one here. Okay, let me just talk about it. Yeah. And the answer itself is pretty simple, of course. The structure is very simple. But I think it's really to link it to what's happening over here in the problem itself. So let me talk about it. Let me just get prepared for that. Give me one moment. And let's now take a look here. Okay, so we have some Boolean. So this is basically what's going to happen here. So you can think about the transmission, but because this is the very initial, most abstract model for the transmission, so you can think about as soon as the transmission occur, we're going to go from here into here. So think about this is like a pre-state, this is like a post-states. So this is more like a pre-transmission. And this one here is more like a post-transmission. And there's a Boolean variable to record whether the transmission has been completed. So in the pre-transmission, B is simply going to be false. And here B is going to be true, whether or not the transmission has completed, right? Let me just double check over here. Yeah, exactly. Okay. Okay, so think about the B over here is about whether or not the transmission is completed. Right? So what we are thinking about is, before the transmission, everything that should be transmitted is still on the sender side. Right? So that's why you can see here, we say, so what we get is basically just F, right? And F is not empty, right? You can see we still got everything here. At the same time, G over here is empty, right? Because G has not received anything yet. But after the transmission, sender side, whatever they have transmitted, they haven't added any new contents yet. So F remains to be what used to be the F. So you can think about F prime simply equals to F, right? But on the other hand, over here, the G over here after transmission, you can see G has now become basically what used to be the F, right? So G here and G here, right? Going from empty to whatever that used to be the F over here. So now if you go back to the invariance there, we're basically saying, depending on whether or not B is actually false or true over here, the contents for the sender and the receiver will be different, right? So the one that we have for this question here is about the receiver, right? So you can see when B is actually false, in that way, we have not transmitted anything yet to the receiver. In that case, G should be equal to empty set. That's really talking about over here, when B is actually equal to false. So, Pawan, does it make sense to you for this one here?
Yeah, it makes sense. I think like I didn't understand what is B and G.
Okay, yeah.
And that was my concern.
Yeah, sure, no problem. I think gotta be careful, because what I just described is definitely something not complicated, but that's something you will be expected to infer from the problem description itself, right? So I would say during the exam on Sunday, you might be seeing some new problem there. The problem itself is not difficult, but I think you just have to be patient and try to read, highlights the key phrases in the problem description and see exactly what's the requirements and what's being asked. I think also visualize what's happening here. So I think that's going to be useful for Sunday.
Okay. That's right. Thank you so much.
No problem. All right. All right, guys, next question, please. Okay, from the chat. Guidance on how to find a trace to prove or disprove a variance. Prove or disprove a variance. Okay. I can give some general guidance. Okay, sure. So find a trace. By the way, you cannot find a single trace to prove a variance, because because a trace is only a single witness. And to really, okay, how about this? Let me write it down. Okay, first of all, conceptually, this is wrong to think about. A single trace, even if this witness shows that the net and var properties are satisfied, it's not sufficient. So think about what's really being shown over here. We are saying that for every possible traces, let me sketch a little bit informally over here, but to get you the idea. We're basically saying for every possible trace for your model over here, you want to make sure the net and also the var property of the variance should be satisfied, right? That's for all. In order to really prove the for all, a single trace is not going to be sufficient. So if you only find a single trace, you cannot prove formally the variance. You can only get some idea about, at least for as far as this trace is concerned, the variance is not invalid. That's all you can say. All right. So a single trace can only give you some intuition. All right. To really formally prove it, you have to really use the two proof obligation as a sequence, right? To prove a given variance, you must state the net and var proof obligations and prove them. That's the only way to actually prove it. All right, that's number one. On the other hand, how do we disprove a universal quantification, which we spoke about, during the math review lecture? In that way, you only need to find a violating trace, right? So that's why, for example, let's talk about life lock. So the way I kind of show you that the system is not life lock free is by showing you a witness violating the life lock freedom property. By showing to you, in this particular trace, we got some infinite tracing, we got some infinite interleaving of the new events. So that's a violating witness. That'll be sufficient to disprove that the system is life lock free, if you think about it, right? So that'll be the second point to make. So that's point number one and point number two. To disprove a variance being valid or appropriate, you can find a witness trace which violates, because in order for that variant to be valid, it must satisfy both the net and also the var properties. So if you can find me a trace that shows to me either it violates net or it violates var, that'll be enough, because it doesn't satisfy both. All right. So for example, let's say if you can give me a trace, imagine that this is a trace. If somehow you can show me that between these two consecutive occurrences of the new events, if it is not the case that the value for the variant is strictly decreasing, if it is not the case, then you find some violation. Or maybe when you are trying to find maybe after this particular event occurrence, somehow the value of the variant becomes negative, that's also a violation. You just need to show me one of them, right? That's how you show or disprove the variant being inappropriate. All right, so that's something very important to clarify. That's also linked to our general strategy about proving or disproving logical quantification, right? That's something you may want to review as well. Question 6 about test number 2. Okay, about guard strengthening. Sure. Okay, let's now go to question 6. Okay, so I'll still leave written quest 1 over here handy. No, actually I can come back later if necessary. Written test 2. And then, okay, question 6. May not be question 6 from my end, but let me just go to here. But I might know which question you're talking about. Okay. Give me one moment. Guard strengthening. Billy, not this one here, right?
No problem.
This one?
Yes, Prof.
Okay, good. All right. Okay, how about this? let me talk about it in a more intuitive manner, but the detailed explanation is also here. You can also go over, but I'll show you what you should really watch out for this one here. Okay. The most important thing about this one here, okay, let me just copy this and I'll show it to you. One moment. Okay. What's happening here? Oh, you know what? At the same time, we also got, so this one is about de la freedom, right? So we're talking about,
Yes, ma'am.
yeah, de la freedom. Yeah, just want to be sure. De la freedom.
Sorry, I was.
No, it's okay. De la freedom, right? So let me just do one more thing and then we can talk about it. Okay. So let me just go to de la freedom. Okay, I just want to copy the proof obligation over here. Okay, there we go. That's the de la freedom. Okay. Okay, let me also paste it over here. All right, there we go. Okay, so since we're talking about de la freedom over here, and the question itself, let's be careful. Let me point out to you. That's why you got to be very careful when you read the question. It may impact the model's de la freedom condition, right? It talk about the goal. It doesn't talk about the entire proof obligation, all right? And we also spoke about the intuitive notion about de la freedom condition, in the lecture. That one you can also review. So this is really the de la freedom condition the question is referring to. This is the deadlock freedom condition. On the other hand, you can think about the axioms and the invariants. They are not relevant as to how we formulate the de la freedom condition, because the de la freedom condition only depends on the guards of every individual event. So whenever you want to change anything about the axiom or anything about the invariance, it's not going to impact the way you formulate the de la freedom condition. The only way for you to impact the de la freedom condition is by modifying the guards themselves. All right, so that's a very important thing to understand first. So this is not relevant. Irrelevant to de la freedom condition, right? So that's why when you look at the options there, if there's any option that's about, for example, changing the invariance, adding, removing an invariant, and also similarly for axiom, they simply wouldn't impact the de la freedom condition, so they will just remain the same. So for any option like that, that's to do with the axiom and invariance, the answer should be they remain the same. All right. On the other hand, we can talk about exactly how to understand. I'll give you one example here, and for the rest, you can definitely go over the answer. So let's say this one here. All right, let's say this one. So before the change, we know that the deadlock freedom condition is going, okay, nothing to do with the axiom and invariance, but we only have to do with the disjunction of the individual guards for the events G1 or G2, right? So this one is for event number 1, that's for event number 2. And after the change, the de la freedom condition is gonna be different, because now we are modifying the event 1's guard from G1 into G1 and P. So think about it's going to become, okay, used to be G1, but now it's going to be G1 and P. So we effectively strengthen strengthening the predicate over here. So this is a predicate, and this is another predicate. Obviously, this one here is stronger than the predicate over here. So we will say that it's going to become stronger for the de Freedom condition after the change. Billy, are you okay with this?
Yes, bro.
Okay, so basically that's how you're gonna look at every option there. That's not to do with invariance or accident change. It's okay if I leave you to that, or you want to go over some options.
So stronger and weaker just means the condition itself. It doesn't mean that we will be able to prove deadlock.
That's correct. So the stronger, weaker is just about the predicate itself. So we are talking about the predicates for de Freedom before the change, and also the predicate after the change. You're comparing these two predicates to see if you can determine which one is stronger. That's all we are asking.
The thing that I had trouble with.
Yeah, so we are not talking about the easiness of discharging them. We're only talking about whether the condition has either become stronger or weaker. That's all we are talking about.
Okay. Thank you.
Yeah, no problem. All right, guys, anything else? Okay, I'll pause a little bit more, a little bit longer, just to see if you guys got more questions.
Yes, sir.
Hajab, go ahead.
Yes, sir. For the exam, will we be given the structure for let's say M1 or M2, or do we? I was put to memorize the event.
I'll say, yeah, I see what you mean. So for the exam, if there's any breach controller question you will be asked, you do not need to memorize or put any specific model details, like what the event should look like or what the variable should look like. So I will give you, when appropriate, something like this. I'll show to you exactly. Let's say, for example, let's say if I ask you some specific question about the M0 we discussed in the class. Give me one moment. Okay, so let's now take a look at this. Let's say take M0 for example, which is here. Oh, there we go. Okay, something like this. So if I ask you any specific question about the version of the or any modified version of the bridge controller, I'll give you a complete listing like this. So you don't need to memorize the detail. You don't need to.
Okay.
On the other hand, it doesn't really mean you don't need to understand the rationale behind how the model has got to that complete stage. For example, let's say, so I'll give you details like this for sure, but you have to understand why the guard should be designed this way and why the action should be designed that way, etc. But I'll definitely give that listing to you. Yes.
Okay. That makes sense.
Good.
Thank you.
No problem. All right, guys, anything else? Okay, something about disproving a variance. How can we identify the events that will disprove it? It's a very good question. It's basically the same question as, let's say you got some invariance in your model. How can you identify the trace that's going to violate the invariance, right? So it's basically a general question like how do you disprove a universal quantification? You basically have to somehow think through all the combinations of the variables somehow abstractly, and then to see how I can have some combination that's going to violate the property, right? That's a general tip. But exactly how to do it, it's hard to describe the process. You just it's more like a trials and errors process, really. So you may just want to say, okay, maybe after the init events, what events are possible, right? Maybe after init, I can do ML out. Okay, after ML out, what are my options of the event that's enabled? After ML out, I can do maybe ILN, or I can do another IL out and see how these combination, if any branch of the trace is going to give you some violation of the property, right? It is a trials and error process. There's no magic here. You gotta also spend some time working out the working out the exactly how to lead to that violation. Yeah, but just something to for your information. In 4315 next turn, we will see actually a tool that's going to somehow help you automatically find some violation trace using another paradigm of the former methods, but that's only for next turn. All right. All right, guys, if there's no more question here, I might just leave the study back to you. I'm going to make the recording available as soon as I can. Hopefully, briefly after lunchtime, right? I'm going to process the video and I'll post it. All right. And best of luck to the final bits of preparation for your exam. And then I'll see you all on Sunday. All right. Guys, thank you so much for coming. I appreciate it. And then hope that helps. And I'll see you all on Sunday. Be well.
Thank you, sir. Thank you.
You're welcome. Bye-bye. Be well.